Hey everybody, it's Grant Sims at Chief River, talking security, talking about hashes today. Um, what I wanted to discuss is, what hashes are and where you might find them in computer systems. And in my mind, when I hear hashes, the first thing that comes to mind is passwords. You might have heard of, cracking hashes, or maybe you heard of, passing the hash. And so I wanted to talk a little bit about passwords, and then we'll look at another concept where hashes are used from an integrity standpoint and how it's applied with digital signatures and email. So first, here we are looking at how passwords are crafted and stored, and this is using a example Linux system for how that works. So what typically occurs is you'll go to set your account up. It'll ask you to input a password. You will take that string, the system will take it, and then typically will add a salt value. This salt value is important for combating against rainbow tables or hash tables where they pre-computed a bunch of hashes to try and improve the efficiencies of cracking hashes, as well as if you have accounts with the same password. It'll compute a different hash, and therefore you couldn't tell that passwords were identical across systems or accounts. So anyways, they'll take the password string that you provided, the system will craft a random salt, and it'll append those two together and then use a hash function like SHA-512 to actually calculate the one-way hash. Remember, hashes are one-way. That's why they're great for passwords, because the system doesn't really care to know your actual password. It just needs to be able to verify that you, the authenticator, know that password. And then in the event of a compromise, these can't be reversed. It would take someone to try and crack them, and if they're strong enough and using a strong hash function, that should be difficult or impossible. So, like we said, we had the password string. The system added a random salt to it. It put those two together, and then it hashed it. And the outcome will be what you see here in red. This is the hash, the one-way hash of the password that you provided and the salt together. It'll also store the salt value in the line there in the Etsy shadow file as well, for the later step, which is actually verifying that the authenticator has the correct secret. So we've got this stored, the system's good to go. Now let's look at the actual process of how it verifies that the authenticator knows the secret. So now we're coming back into the system, it's asking us for our password, we type in our password, we press enter. When we do, it's actually going to take that user ID and go look up the salt value. This salt value is in clear text in the Etsy shadow file. It'll take our password that we provided, our input, it'll add the salt to it, and once again it'll hash it. And once it does so, it'll produce the one-way hash. As long as we typed in the password correctly, those two hashes should now match. So the system will then compare the hashes and show, hey, these do equal each other, and therefore it is a success and authenticate you. And we can quickly kind of show this just using OpenSSL here. So let's just echo a password. We'll echo, this is my password, and then we'll use OpenSSL to create a SHA-512 hash from that. And this is the hash we get. Now we said, a system will typically add a salt. So let's add a salt to this. I'll just type in a generic addition there. So now we've added the salt. And you can see that these do end up with different hashes, because at the end of the day, this is a different value being provided. So just remember that when the system went to authenticate you, it would take your password, it would look up the salt value in the Etsy shadow table for that user ID, put them back together like this, and simply run this command again, in essence. And as long as these two match, you would then be authenticated. I hope that was helpful for just understanding the basics of how systems store and utilize hashes for authentication. Now let's move over to a little bit more in-depth scenario where we're using both hashes and public-private asymmetric keys for email digital signatures. So this is our second use case for hashes. Remember, hashes are one-way functions. They're great for proving integrity of things. And in this case, in email, it'd be great to have integrity. If someone sends you an email, you would like to know that that email came from the person you believe it did, it was not spoofed, and you would also like to ensure that the contents weren't tampered with as it traversed the internet. So at this first example here, we have John, who's the email crafter, and we have Bob, who is the receiver. John crafts an email, sends it to Bob. Now, Bob has some questions when he's looking at this email. Did the email really come from John? And is this really what John wrote, or as it traversed the internet, did someone tamper with it? So hashing can help us here. As John crafts the email, he crafts it, and then he will compute a hash, simply, very similar to like we did with our password. This will create a one-way hash value, which he could then share with Bob. When Bob receives the email from John, he can then compute his own hash and then match those hashes to see, is this what John sent me? Now, this line is difficult. How did the hash get from John to Bob? Does he know that hash actually came, or was that actually tampered with as well as the email, proving this, invalid from solving our questions here? This could be over the telephone, and Bob could be doing some verification because he knows what John's voice sounds like. So he's relatively sure that this is John giving in the hash and then checking the hash himself and comparing those values. But taking it a step farther, we want to use digital signature to really improve upon how we get the hash over to Bob to be sure that, one, it is John sending the email, and two, the message has not been tampered with. So a prerequisite to this is some type of public and private key pair and some type of repository to ensure that those public keys do belong to the users that we believe them to. So this could be using PKI with a certificate authority, or similar to like PGP, we could be using a web of trust concept. But just know that we have public keys that are in the public that we can grab, and we are relatively sure that these keys, these public keys, do belong to who we think they do. So in this case, John has a public and private key pair. He's posted his public key out there, and he's kept his private key stored securely, and that only John can have. And Bob is able to pull down this public key, and Bob is very certain that this is John's public key. So now we're going to go through this scenario again. John's going to craft an email. That email is going to then be hashed, and he's going to get a hash value of it. And now we're going to use this hash value in conjunction with public and private key pair to encrypt the hash with John's private key. Once we've done that, we can then add that as an attachment or part of the email header, and we can send the email over to Bob. Now, Bob receives the email and an additional thing, which could either be a header or an attachment of this encrypted hash value of the email. So what Bob's going to do, Bob's already got John's public key. He's pretty sure this key does belong to John, and he's going to use it to decrypt this attachment or header. And inside that header, we're going to find the value, the hash value of that email. Now we can then ourselves go along and run a hash value of the email and compare them once again, similar to up above. And we can assure that, yes, this email did come from John because we used John's public key to decrypt this hash value. And we can ensure that this is what John wrote and it hasn't been tampered with because the hash values match from what we locally computed and what was provided in the encrypted attachment or header. Now, when I was first doing this, I kind of thought, well, why do we even do the hashing? We could just be relatively assured this if we just encrypted the whole email with the private key and use the public key to decrypt it. Why are we involving hashing? And we could do that, but it's inefficient, not as secure, and it's computational expensive. So what I mean by that is Hashes are a fixed length. Doesn't matter on how much data is in there or the size of the data. It will be the same length regardless. So we can really keep the size down. If we were to do the whole data contents of the email and the email was super long or included a lot of files, attachments, that public-private key encryption could be very large and therefore takes more resources to compute that and use that as an integrity check. So really, the two together work nicely where hashes are meant for integrity. They're standard size. They're easy to compute from a computational perspective, and that's what they're meant for. They're built to avoid collisions, improve integrity. So hopefully that was super helpful and kind of breaking down how we can ask those two questions and validate those two questions when Bob receives an email. Now let's look at it from a little bit more of a practical example or getting down to the command line. So what we're going to do is we're going to kind of do what I just showed in that example, all locally here. So let me pull this over. So first what I'm going to do is I'm going to generate a private key. Next, I'm going to create a public key derived from that private key. As you can see, we now have these two. I can actually show these. And I would never do this with a true private key, but just to show you the contents, that is our private key and our corresponding public key. And mathematically, just realize these are binded together. All right, so we have our public and private key. Now what we want to do is just create a sample file, a sample text file. Inside the contents will be hello, comma, world 2. We can less that out. There is our file. And now we want to digitally sign this. So we've digitally signed this. We've used our private key to sign it, and we outputted the signature.bin. This is what could be, part of the attachment in the email. And we did that, on top of our sample.txt file, which could represent our email. So if we ls, you can see we have our private key, our public key, our sample file that we wanted to sign, and then the signature for this file. Now let's compute our own local hash of this sample.txt file to see what it would be. So we're using OpenSSL, saying, give us a SHA-256 hash of this file, and there is the hash. Now what we're going to do is we're going to look inside this signature bin. This is a binary file, but we're going to look inside of it, and we're going to pull out the hash that has been encrypted with the private key to see if it really matches this, to see how that works under the hood. So once again, we're going to use OpenSSL. We're going to look inside the signature. We're going to use the public key to decrypt this signature. And then we want to output the last 32 bits because that is where the hash exists within this binary file. And as you can see, looking at the hex output, here is our original hash that we calculated locally. And then here is the identical hash that was pulled out from the binary file that was encrypted with our private key. So there, in fact, you can see a little bit under hood of how this is working, and hopefully that was helpful connecting the dots from a generic understanding of it to how these things are actually working within the system. If you have any questions, please reach out. Please put it in the comments. Thanks as always, and appreciate your time.